Hi, everyone. Thanks for coming to the Kubernetes control plane for busy people who like pictures. If you saw my previous talks or you looked at the slides online, you know what's in store, OK? OK, a little bit about me. I'm Daniel Smith. I'm a staff software engineer at Google. I've been working on Kubernetes since before it was open source. I am the co-chair, co-TL of SIG API Machinery, which owns API server and controller manager and like a lot of the control plane of Kubernetes. So who is this talk for? This is for two groups of people. If you have ever considered building your own control plane, I'm sure like everybody does this, right? If you've ever thought about this, this talk is going to be a survey of the existing controllers in Kubernetes. You can look at those, and together we're going to learn what patterns are good and what patterns are a little harder to understand, maybe. And you can decide whether your problem domain is a good fit for this style of control plane architecture. The other group of people that I'm targeting this at is like, you know what a pod is, you know what a deployment is, you're ready for 201. So we're going to do that. We're going to go through like every controller in the system and say what it does. We're going to have fun. We've got a lot of slides to go through. OK. If you saw my last two slides, or my last two talks, or even if you didn't, this talk completes the trilogy. I didn't know it was a trilogy when I started, but it is. So I'm going to reference those a couple times. You can go see videos on YouTube. Don't worry, you won't have any problem understanding this. So if you've seen those, you probably heard me say something like, the Kubernetes API is about humans and machines working together. Well, you can't do that without some machines. So this talk is about controllers. Controllers are the things that make it all work, the ghost in the machine, the person behind the curtain. You get the idea. And before we like dive into the controllers in Kubernetes, I want to, everybody loves control theory, right? I want to talk about control theory for just a little bit. I'm going to start off by rehashing the age-old debate of state machine versus control loop. The argument goes like this, and we actually rehashed this argument in a number of places early on in Kubernetes, and we came down pretty firmly on the control loop side of things. But the argument is like if you're constructing your system in terms of state machines, for every like binary variable, you double the number of states. So if you've got to write things that get every action perfect, you've got so many states. Like you can't possibly get it all right. The number of states grows really big as you add variables. And to make it worse, like not all the variables in the system are binary, right? We've got real numbers. It's not good. That's the technical term. So if you instead factor your logic in terms of controllers, now you're not talking about states. You're talking about like clusters of variables. This is the input to your controller, the status, the other things going on in the cluster. And now you just have to add an additional controller to handle every cluster of variables, right? So the number of controllers just scales sort of linearly with the number of things going on in the cluster. In a prior talk, I talked a lot about the Kubernetes resource model, like the API, how it lets you, gives you a constant way of performing API actions on the cluster. And that was about integration complexity, right? If you know how to drive one Kubernetes resource, you know how to drive them all because the API is constant. There's even constant metadata. Whereas the controller half of it, the half that I'm talking about in this talk, is the implementation complexity, right? So there's the API, we factor everything to make it simple. But controllers, we also factor the logic of the controller to concentrate the hard part of the controller into one place. This makes it globally easier. Like there's no single state that you have to worry about. Like there's no, to make a change in Kubernetes, you don't have to have every single possible state in mind to make a correct change. But it makes it locally harder because your controller has to be written with all possible, like everything else going on in the cluster, you have to take that into account when you're writing your controller. So let's talk about some things. Let's talk about Kubernetes resource model controllers. In doing this survey, I came up with a list of things that I think make a good controller. Only do one thing. Have some clear input source. Like people need to know how do you make it work? How do you drive your controller? Have a place to write status. People need to know if your controller is happy or healthy or unhappy or how's it feeling. you need to have an output place, like what are you actuating? What is your controller doing? And then the last two, I think, are maybe the least obvious and possibly the most important. The controller has to anticipate its own effects, like the effects of its own actions on the rest of the system. And when you are having a problem, break things a little bit. Don't break things a lot, just a little bit. And don't pretend things are not broken. So let's talk about those last two a little bit more. So here we have a Kubernetes controller in its natural habitat. And I want to zoom in on inside, see what's inside this controller. So if you zoom in on a controller, you'll find like there's a lot of plumbing, and there's flags and configuration, and there's all this stuff like informers, like who knows what, commented out code you don't want your coworkers to read. But there's also some logic in there, right? There's some brains, like there's some like if this didn't do that, something is active there. And if you zoom in on that, what you'll find is the controller has to have a model of its environment, right? It may be implicit, it may not be explicit, but it is there. And controllers have to have a good model of their environment to do a good job at controlling the thing that they're trying to control. Like a concrete example, if you're the Replica Set controller and you're trying to make pods, and you make 100 pods, and then you look and like you need 100 pods, so you make another 100 pods, and then you look and you have 200 pods, and you're like, oh my god, I have 200 pods, delete 100 pods, and you look, you still have 200, like it'll oscillate, right? So you have to have a model of what you're doing to the environment. And some simple controllers don't necessarily need to do too much. It's like, okay, I set the thing is set, like that's it. But there is some sort of implicit model. So if you zoom into the controller in the model, there doesn't have to be anything in there. You don't have to go that far. Take a deep breath. You're okay. Okay. And so the last thing about break things just a little bit. Well, I want to talk about like how do changes propagate in a Kubernetes cluster. So you do something as a human or as a CI/CD system or something, and then your controller goes out and does something else, and then maybe more controllers go out and do other things, and so that propagates. And eventually, like, the system quiesces. It comes to a quiet state. It's happy. Nothing needs to change to get into a good state. That's one way changes could propagate. Another way changes could propagate is like you trigger a controller, which then triggers something else, which then triggers something else, which is like it goes in a circle, right? That's another way that your change can ripple through the system after you write a change. There's another way, which is like you make a change and then like you've got a cascading like failure and like controllers keep writing until API server can't keep up anymore. So you don't want to do this. Like if you do this, your control plane can't keep up. Something bad is going to happen. I'm going to say like this is actually how you want your controller to fail. You want to do this really slowly. And the reason why you want to break things a little bit is because it gives signal to other things running in the cluster, right? Like if you create 1,000 unschedulable pods, maybe you have a problem. If you create 1 million unschedulable pods, you've got a big problem. But if you create 100 unschedulable pods, that's a signal to something else in the cluster. Maybe you're running a cluster autoscaler, which is like, oh, it's time to add a node. That one, we'll hit that one in a few minutes. So it gives signal to the rest of the system. If there's self-healing components, they can fix your problem for you without the controller author really having to understand what it is that's fixing the problem. Okay. So in summary, yeah, break things a little bit, anticipate your own effects. That's really the important one, anticipate your own effects. Okay, that's enough theory. Take a deep breath. We're done with the theory. It's time for control practice. And what we're going to do is we're going to spend like a few seconds on every controller in the system. I've classified them here into three categories. The classic controllers, like the things that really look like a controller, if you go read the Wikipedia control theory page, which I recommend is good. The standing query or table join controllers, and the injection or bijection enforcers, okay? We'll clarify what those means in a second. Let me give you just a few disclaimers before we dive in. Many controllers write events. If you've used Kubernetes, you know what events are. I'm not going to show that on the slides. It makes everything really messy. Likewise, many controllers have some way of writing status. Sometimes I showed it because it's important. Sometimes I didn't. If you need to know more, you can always go read the code or the API or whatever. I'm going to go fast on some of these controllers. I'm going to go slower on others, just depending on whether I think it's instructive or interesting. So Here's our first group. It is the garbage collectors. This is like the scenario is you've got too much of something and you need to have less of it. So this is the theme for this group of controllers. First one is the pod garbage collector. It's basically like you've got too many finished pods in your cluster, so let's go get rid of some. This is a pool skimmer. Like you've got too much water in your pool, let's drain some water. Next is the namespace lifecycle controller. It's called the lifecycle controller, but actually all it does is delete things inside a namespace when the namespace goes into the deletion phase. Next is the actual garbage collector, and I'll spend a minute on this one because this is really great. It frees your regular controllers from having to tear down the structures that they make, because you set up the parent pointers on your objects. There's a metadata field, and then the garbage collector just sits there and watches. And when the parent objects go away, it'll delete the child objects and free up your whole hierarchy for you. If you've looked at I don't know, replica set code or deployment code before we added the garbage collector, it actually is a significant amount of work to clean up everything correctly. So this is great. Please use it in your own controllers. Yeah. OK, so next we have this triplet of certificate signing request controllers. And this first one, these three controllers work together to provide a feature, and that is sign certificates. So a user makes a certificate signing request, and then various things happen to it. And this first controller that I'll talk about is the Csr Cleaner. That basically deletes certificates, CSRs, after they've expired, or after they've expired, whether or not they were signed. These controllers are really good examples of the do only one thing principle. So yeah. OK, next up is pair, the persistent volume and persistent volume claim protection controllers. We have this tool in Kubernetes, the finalizer. How many of you have heard of a finalizer? OK, good amount. A finalizer is basically you put a tag on an object, and the object can't be removed from the system until something else comes and removes that tag. Right? It's called the finalizer. So the persistent volume controller and claim controllers, they set up these tags because you have a matching volume and claim. These have references to each other. We don't want to remove one and leave the other one dangling. So this puts finalizers on both and won't remove the finalizer until they've been cleaned up properly, right? So it's a way of adding some referential integrity. Let's see. Yes, the TTL after finished controller is basically a time-based garbage collector. Right now it only works on jobs. I think there's plans to extend it into make it more generic in the future. OK, so that's it for garbage collectors. I'm sure you are ready for something else. This is the Replica Set Controller, which I think is the first really true controller. It's exactly like a thermostat. You can make less pods, make more pods. Yeah, but this is the first thing you see when you learn Kubernetes, so I'm sure you all know about this one. So let's go to the deployment, which is a little bit more interesting. I think of this one as a thermostat programming robot, right? So it's where the replica set automates keeping the collection alive. The deployment automates rolling between two collections, right? So it's like a robot that turns down one and turns up the other. Okay, and a similar one is the horizontal pod autoscaler, which reads metrics about pods and uses that to decide, do I need more of these things or less of these things? Are they loaded or not? And it can work on resources that support the scale sub-resource. So again, it's a generic, if you use the thing, this HPA can scale your collection. And finally is the well, I don't know if it's final or not for this group, but this is the cluster autoscaler. And basically, if you've got unscheduled pods, it will add nodes. I think it's not available on all cloud providers. But there's no reason you can't write one. And this is under the theory, is there too much water in your pool? You can solve the problem by making your pool bigger. OK, so the second set of controllers is the standing query or the table join. And we're just going to dive right in. This is the endpoints controller, which is, I think, maybe the first controller that was written after the controller infrastructure got up to the modern concepts with an informer and stuff. And it basically watches services, watches pods, matches the two up, and writes endpoints. And then the endpoints feed into the DNS resolution the kubeproxy component so that you can access the other thing, the pods that implement the service. Okay, next up, I've got a pair that work very similarly. The controllers are the pod disruption, the disruption controller, and the resource quota controller. And they both work by observing things and updating a status, and then they have an API server component that acts on that. So the disruption budget counts pod disruptions like getting evicted or something like that. And I think I labeled it an emission plugin, but it's actually a sub-resource, the evict sub-resource. Looks at that thing to know, like, is it safe to perform another disruption on this pod? The resource quota does something very similar. It's like the easiest one to explain is just counting things, right? Like you put a resource quota object in that says, you can only have 100 pods. And it like counts up the pods and says, OK, you've got 99, so that the admission plugin can act on it and know whether it's safe to add another pod. I mention these because they are an example of a controller working with a admission plugin to provide some sort of safety, something about the cluster. They're doing things that you can't do in an admission plugin because you don't want to do you don't want to do a linear scan over all the resources in the cluster before admitting a pod, right? You need to cache that. That's what these controllers are for. And next up, we have the CSR again. This is the Csr Approver. If a CSR comes in and it is from a node, this thing approves it. Why did we do it this way? It's so that you can use the system with sources other than nodes. So you can, as a human, you can make a CSR, and you could have, like, maybe your system administrator could approve it, right? So the controller is like, it approves the CSRs that it knows about, but you can use the system for other things. And this particular CSRs in question is we're getting kubelet access tokens to API server so it can participate. Next up, another part of the auth system is the cluster role aggregation. So cluster role is part of the RBAC system. And you can put in a list of rules, like this role, like the reader or the viewer. It can like get pods, say. But it's not nice if you have to, like somebody adds a CRD and they're like, well, really, the author of the role didn't know about my CRD, so how can this work? We have this, it basically takes a selector and it looks up cluster roles that match the selector and copies them into the cluster role with a selector, right? So it can either have a rule list or a selectors, like copy your rules from these guys. This one, I think, I would say it's maybe not the best example of the like, it uses its input and output location as the same. I think it's a little confusing. So I would recommend, like, if you're going to learn something from it, learn, like, maybe this would have been better as like a two-step object. OK. Next up are the injection or bijection enforcers, and I'm probably going to use the word injection just because I don't want any math majors to come give me a hard time afterwards. It's safer. First up is the Daemon Set, which is maybe just the classic example of this. Like, a Daemon Set is like, this is a node description, this is a pod description, and then the controller, all nodes that match the label, it adds a pod. All nodes that don't match the label, it makes sure that this pod doesn't exist there, right? So it's a bijection. Sorry, it's a lot of talking. This is the service account controller, and it's very simple. Like, it sees a namespace, makes a default service account in there, like literally a service account named default. And this has a sibling controller, which sees a service account, and it makes secrets with a token that has like an API access token. It adds a reference to the service account. Like, this is all in service of getting your pod running in the cluster and API access token, so it can make calls to API server. This is what drives that under the hood. So it makes the secrets and puts a list into the service account so that we can rotate the secrets. So that's why it's a list and not just a single one. So this is maybe, I don't know, this is maybe the most entertaining header of any file in the Kubernetes code base is the persistent volume binder. It's got this very entertaining blob about how it's written in space shuttle style. and all branches are considered. And so this is not a good example of the do only one thing, because it does like 4 things. But it is a great example of considering all of the possible effects and writing a really good controller that like all states that the cluster can be in are handled by this controller successfully. And it works well, so I can't complain about it. It basically matches up, like you make a persistent volume claim, we have to find a volume to bind to the claim. It finds a volume, but you can actually, like, the system can allocate volumes for you. So then you have to allocate the volume in the availability zone where the pod is going to schedule. So it's like, does this dance with a label with the scheduler? It works. Okay, and now we have a sequence on what I call the candy wrappers. They're like a bijection of, or an injection of one thing, basically. So CSR signing, like every time it sees we're going to go through fast through these. Every time it sees a CSR that is approved, it signs it. The node, the TTL controller, which is, the name is not helpful. It's actually managing how long nodes will cache secrets and config maps based on the cluster size. It just, every node object in the cluster, it sets an annotation. The node IPAM controller sets up the IP address ranges for pods that go into that node. Maybe it gets it from the cloud provider. The node lifecycle controller, it observes conditions on the node and sets taints, which like keep pods from scheduling. And also, if the node goes too unhealthy, it will evict the pod. So like, if the node isn't around to like manage itself, we have to have a backup controller come in and manage things for it. And I will point out in this one, it's a good example of like bridging, like understanding the node conditions and turning those into a set of things that the scheduler can understand, right? So the scheduler doesn't have to understand like low disk state or something on the node. It can just look at the taint. The cloud node controller is for initializing nodes. They come up with the cloud taint, this thing takes it off, and it puts cloud-specific properties on. The root publisher is yet another part of the security process. Your pod, when it comes up, it has to be able to trust API server. API server presents a cert. This has the CA that lets the pod, the workloads running in the pod, validate that the API server cert is valid. And this controller makes a config map in every namespace with this CA, which can then be mounted into the pod, into the standard location on disk. Next up is the scheduler, which I called it a candy wrapper. It's maybe the most complicated controller in the system. It is a controller. I just listed the things that it looks at. Maybe it looks at more that I didn't see, but I'm not going to explain that here. Okay, we're getting close. Bear with me. There's a lot of controllers. This is the scheduled job controller, which is like you give it a job and like a frequency, and it like just waits for that to come up. I like to think of this as injection with the phase of the moon. Next is job itself, which is the injection is complicated. The thing is just running a pod, so that's not too complicated. But you have to run it in like you want n total, and you can only do m at a time. So it's kind of like baking cookies in an oven. Like you can only fit so many sheets on, and maybe sometimes the cookies burn. And yeah, so that's that. In contrast to the stateful set controller, which is more like a babysitter, where the injection is very simple. It's like you're going to make 3 of these things or whatever. But the thing that you're doing is very complicated because you've got to make a persistent volume claim and a pod and like match them up and like what if they go down and you restart them as order. So yeah, that's a complex thing. Similar to Kubelet, which is also doing a very complex thing with plugins and the Node OS, and like it's got to update pod status and node status and read secrets and config maps. That's complicated. Okay, almost done. This is the operator pattern. You may recognize it from one of my previous talks. And this is like the canonical way of bridging a legacy system and providing an interface that works natively with Kubernetes API clients. And like we actually have some controllers that are essentially this. The first one is the service controller, which updates, allocates and updates load balancers. The route controller programs the network fabric in the cloud provider. the node lifecycle, the cloud node lifecycle provider controller. If your node goes unhealthy, it checks to see like, does the cloud provider still think that this node should exist? And if not, like maybe I'll just delete it. And the node problem detector also falls into this category, where it's like observing the operating system on the node and writing corresponding conditions to the node object. Okay, that's all of it, most of them. Do you feel ready to write your own controller? I really appreciate you coming to this talk. I think this is a really fun problem space, if you agree. We'd love to see you in API Machinery. Some of these controllers are owned by SIG Apps. SIG API, SIG Architecture owns the overall vision of the system. Yeah, and as always, my team is hiring, so yeah, cool.
We have time for a few questions. Thank you, Daniel.
Thanks.
Please raise hands. Who has questions? All right.
There's no questions because I said all there is to say about these things.
Right. They have to read the code before they ask more.
Yeah, the next level down is like, yeah, you've got to read a lot of code.
Hi. So are the controllers pluggable? Are the controllers pluggable? Can you add controllers? Can you remove controllers at will? Can you choose which controllers you include in your Kubernetes cluster?
Yeah, the question is, can you choose which controllers run? Yeah, you can. There's a default setting. There's a enable flag that which you can choose to disable or enable controllers. If you look at the man page on Kube Controller Manager, it'll tell you.
Okay. Sorry. Okay. More questions? All right. Was there a question there somewhere? No? Okay.
Right.
All right.
Thanks, everybody.
Sounds like folks need a break. Thank you, Daniel. Thanks once again. Thanks, everyone. To come back to this room, there will be another talk later on. I believe it will be about server-side apply functionality in about half an hour, right?